Hello and welcome to another video. In this video we're going to be working on sum of two integers. So in this problem you're given two integers a and b and you want to return their sum without using plus and minus. And it's a bit manipulation problem, and honestly it's one that if you haven't seen like the solution or this kind of strategy before, you're probably not coming up with it. Maybe you can do it like one bit at a time. I could see that, but also there are issues of like the signs, but let's get into it. Essentially, for obviously, like we don't have to figure out how to get the output. It's just a basic sum, or you should return a basic sum. But essentially what we're going to do is we're going to write two functions. So we're going to write a function sum, and it will give the sum of two positive numbers. Notice the constraints: numbers can be negative. And we're going to write difference, and it will give the difference of two numbers where a is greater than or equal to b, right? So it's going to be a positive difference, and it's just going to be easier to do. And essentially any two numbers we get, we can always transform them, so we can either get the sum of two positive numbers or the difference where a is greater than b. And the way to do this is pretty straightforward. So let's say we had like two negative numbers like this. What we could do is we are allowed to use multiply, so we could just say like, let's just take -1 times 7 plus 5, okay? And that'll be the same thing. Or if we had like one positive and one negative, let's say we had this. So we're gonna have two cases here. So we always want, like here we're gonna use difference, and we're always gonna want a difference where the a is bigger than b, because we want like a positive result. So the way to do this one would be to multiply times -1, right? So you just multiply by -1, and then you multiply by -1 to get the result. So that is also pretty straightforward. So essentially here, yeah, you would just say like, okay, let's just multiply this. This other one would be like multiply this by this, pretty much. But yeah, essentially this would be the same thing. You would convert, so you'd get 7 minus 5, and then whatever the result you get, you would multiply by -1 again. Same thing here, right? You'd add this, and then you'd multiply by -1 to get the result. So here you'd get 2, and then multiply by -1. So you're kind of like multiplying by -1 to get the format you want, and then multiplying by -1 again to get the final thing. So so you can use all these like -1 tricks. And now the other format would be, let's say you had -5 plus 7, right? So if you had a format like this would work as well to do the difference. So if this was a and b, you would just say like, well, let's just swap them around. And in a sum, you are allowed to swap around values, right? This is equal to this plus -5. And then you could say like, well, that's just the same as 7 minus 5 and so on. So essentially, we're going to always convert our numbers to a format where it's either a plus b or a minus b, where a is greater than or equal to b. So now that we know that, it's just going to be like a bunch of for loop, or a bunch of like if-else if statements, like else-if and stuff. No matter what numbers you get, it's pretty easy to convert. So now let's focus on building this like sum. Like, how do we actually get a sum of a and b? Let's say we have some numbers. Let's say we have like 12 and we have like 7. So essentially our strategy is going to look, if you think about like, how do you do a sum in like a normal sum, right? Like, let's say we have like 12 and 7. Or actually, instead of using 12 and 7, let's use some other numbers just for this. So let's say we have 12 and 19. So there's two parts, right? There is the part of and we can even do this. There is the part of like, what's the actual sum, and then what's the carry sum, right? So normally what you do is you say like, okay, well, there's a 1, and then carry the 1 right here, and then so on. So you can write these out separately, actually. So we can just say like, okay, well, instead of writing the sum and the carry, we'll just write the sum, and then we'll write the carry separately. So we'll say like, this is 1, this is 0, and let's just write the carry part completely separately, right? So this is the sum, and now we have a carry section. And so for the carry, so we carry a 1 here, and then we carry a 1 here as well, right? So something, or actually, we wouldn't carry if this was a decimal. I'm thinking binary, so we wouldn't carry anything here. So essentially the carry would look something like this, but notice this one carry is actually should be in the tens place, right? We're carrying a 1 that goes over here, but this is actually carrying like a 10, essentially, because we put in a 1, but then we carry a 10. So what you need to do is, even though it looks like this, you actually need to shift it So it's going to be 0, 1, and then 1, 0. And so if you add these now, you have a sum, right? I think I screwed something else. I think I screwed something up here, though. Let me see. So this should be 31, right? Oh, right. Yeah, it's because, yeah. So it's because this should not be, like I said, this is not binary, this is decimal. So the sum should be 21, and then this works now. There we go. That's kind of logic, right? We have some carry, and we have to figure out like what our where we carry, and then we have to shift the carry because the bit that makes a carry, the carry is going to be one more bit past that. So now we have 31, right? So that's kind of the idea of getting a sum is we calculate the sum and then we calculate the carry, and we keep doing that until there is no more carry. So let's do that for actually we can do 12 and 19 in binary as well. So 12 in binary is this. And then 19 in binary should be 12 plus 7, right? I think. I think it's actually, okay, it's actually like, not this. It's actually 16 plus 3, right? So this is one bit. And then we have this. There we go. Okay, there we go. So we have 12 and 19 in binary. So, right, 2, 4, 8, 16. Yeah, okay, this is correct. So essentially what we're going to do is we're going to figure out like what operation can we use instead of a plus to actually get these like things added and then but not have the but then do the carry part separately. So it turns out you can actually XOR these numbers to get like the add part, because if you do XOR here, let's just see what happens actually. So if you here you won't even have a carry, so we'll probably do another one. But here, if you XOR these numbers, you will essentially get 1, 1, 1, 1, 1. And you can see, like, if you were to add these in binary, there would be no carry, right? Like, it's all zeros and ones. In order to get a carry in binary, you'd have to get a 1 and a 1. So here, there are actually no carry bits. So this is pretty much it. And then our carry would be 0. And let's figure out, like, what this number is, right? So we have 16. This is 8. This is 4. This is 2. Right, so this is 24, 28, 31. So that is correct. So now let's try another number and hopefully we get some carry bits. So maybe let's do like 12 and like 7 this time. And so this should be 19, so let's try to do that one. So we have 8, we have 4, no 2, so this is this. And then 7 should be this, I believe. Okay, so now let's do this one. And we're going to kind of do the same thing. So we can't add, so we will XOR. So to XOR, we will get 1, 1. And notice this part makes sense, right? So here you're XORing. So XORing and 1, 1 will give you 0. And that kind of makes sense because it kind of gives you the same thing as adding. Because if you were to add these, this add 1, 1 should be 0 in binary, right? Like if you did binary add, the biggest number you can have is 1 in binary. So it should be 0 and then like carry the 1 essentially. And that's kind of the same thing that the XOR gives us. It gives us 0 and then 1. Right? And now we do the carry totally separately. So now we have to figure out how to get a carry without like adding as well. And so remember, to get a carry, the only way to carry something is you would have a 1 and a 1, right? That would let you carry the 1. So to get the sum, we can write this down even. Sum, we need XOR. Then for the carry, we would need a AND operation. And so for AND, in order to get 1, so for XOR, obviously, in order to get a 1, you need a 0 and a 1. For AND, in order to get a 1, you need a 1 and a 1. So let's go through that. So we're going to have 0, 0, then we're going to have the 1, and then we're going to have 0. And so remember that when you actually add this like 1 here, like when you carry the 1 here, this 1 is actually over here, right? So you need to take this, and then you need to bit shift it left once. So we're going to bit shift it left once. So now what we're going to get is we're going to get 1, 0, 1, 1, and then we're going to get 1, 0, 0, 0. And basically keep doing this until the carry is 0. So we're essentially adding, and then we're saying, well, yeah, but like, but what does the carry equal as well? And then we keep doing that until there is no more carry. So now let's try to do that. So first we XOR, so we get 1, 1, 0, 0, right? Hopefully I'm going to do this correct. Yeah. And then we have the carry, which is the AND, which is 0, 0, 0, 1. Okay. And hopefully that's correct. And now we do the same thing where we shift it once. So then we get 0, 0, 1, 1, and then we get 1, and then 4 zeros. So it should be a 0. There we go. Okay. And now when we do the XOR, we get 1, 1, 0, 0, 1. And then for the carry, there are no ands anymore. There are no all ones. So now let's calculate this, and hopefully this is correct, like I said. So here we have 2, 4, 8, 16 plus 2 plus 1. So we have 19. And our original numbers, I believe, are 12 and 7. So that is 19. So that's kind of like the strategy we're going to use for the num. Essentially, we're going to get the sum by doing XOR, get the carry by doing and shift the carry one bit left, because the bit that you're actually carrying should be like a, like just like in normal decimal, right? Like if you have like 12, 19, if you had to carry the one, this one actually is like a tens place ones. It's not a ones place ones. It's the same thing. You're shifting the carry to the left because it is actually representing the one bit farther, and then you just like loop this till carry equals 0. That's how we get the sum. Now let's figure out how to get a difference. And so the difference is going to be like a little bit trickier. So let's say we have 12 and 7 again, right? Well, let's actually think of like our intuitive difference essentially. So let's try to split this up. Let's like do this in decimal again. So let's say we have some numbers. Let's say we have 31, 19 maybe, something like that. So intuitively, let's split this up into what's the result without, like, so for subtraction you have to do borrowing, right? For addition you do carry. For subtraction you have to do borrowing. So we're going to say what's the result without borrowing, and then how much did we borrow? And then we're going to kind of do that until there is no more borrow. So we're kind of doing the same thing as a carry, but now we're borrowing. So here we're just going to say like, okay, well, we obviously can't do 1 minus 9, so let's just pretend we borrowed and then like whatever that is. So we actually want to do 10 minus 9, so we get a 1. And then here we don't need any borrowing. And remember, we're not going to account for borrowing originally. So we will say 3 minus 1, which will be 2. And now we actually have to figure out how much did we borrow. So we borrowed here, right? In order to do this operation, we actually did borrow. And so we borrowed 10, right? But we're not going to represent this as borrowed 10. We're going to represent this as borrowed 1, and then we're going to shift that over, essentially, kind of the same way. So we're essentially saying, did we do a borrow here or did we not? And so we actually did do a borrow here, right? So how much did we borrow? We're always going to borrow like 1 in decimal. And so did we borrow here? No, we did not. So this is how much we borrowed, and then we need to shift that left because we really borrowed 10. We didn't really borrow 1. So that's kind of the same thing with binary. So then you'd say 21 and 10. Then you would do another subtraction, and you'd say, okay, well, 1, 1, and we didn't borrow anything here. And so, is that correct? Looks like it is not. So what did I do wrong here? Yeah, because it should have been 12. Oh, right, I see. So, yeah. So I screwed this up again a little bit. So essentially, this isn't 10. When you borrow a 10, you would get 10 plus 1. So this would be 11. So there we go. So if this was 11, then you would get 2 here. So you get 22, and then you would get 22 and 11. 10. There we go. And then now you subtract them again, so you would get 12. That's kind of the idea, is like, what's my, and you can do subtraction like this in decimal as well, right? Where you're literally just saying like, okay, well, if I need a 10, I'll add a 10. And if I don't, then whatever, I'm going to do it totally separately. And then I'm going to calculate the borrow separately and then keep subtracting the borrow. Because the borrow is like, what do I still need to subtract from my number, right? Just like the carries, what do I still need to add to my number? So now let's figure out how to do this in binary, the same kind of way, right? So let's say we have this, let's just think of some numbers. So I guess we'll go with the 12 and 7 again. So for 12, it's this. For 7, it's this. So the subtraction part, essentially what you are saying is, okay, well, if I borrowed, like, what would my number be, right? Like, where would I need to borrow? So the only time you would need to borrow is if you have a 0 on the top, right? This is A and this is B. The only time you need to borrow is if you have a 0 at the top and a 1 on the bottom. That means you don't have enough. So if you borrow, your 0 becomes a 2, right? You're essentially adding 10, but in binary, you can't add 10. You can only add 2. So you would So when you borrow, or actually, sorry, we're not doing borrow first. We're doing the actual difference. So like what should this equal? Like what should like this part equal? Well, if it's 0 and 1, right? If it's 0 and 1, that means what happened? That means this should be a 2 because you borrowed, and then you subtract 1. So this should be a 1. So what if we just XOR again? Let's try that. So we get 1, 1. We get 0 here, which makes sense, right? 1 minus 1 is 0, and then we get 1 here. And so that works out. So if you get 1, 0, that should be 1. And if you get 0, 1, then you're essentially saying I borrowed, so this becomes a 2, and then 2 minus 1 is 1. It's kind of the same thing. So now we have to figure out like how much did we borrow and where do we borrow. So first of all, let's write that down. So for the difference, the actual difference part, it's just an XOR again. Now borrow, like what should our borrow be? If this is A and this is B, right? So the only time we borrow is if this is 0 and this is 1, right? That's the only case, because the bottom one has to be less or bigger than the top. So only the bottom can be bigger than the top in binary. Is this has to be 1, this has to be 0. So bottom means A has to be false, right? So it has to be not A, essentially, right? Like the A bit has to not be, the A has to be 0. So not A, which will just flip the bit. And B has to be true. And so the only way this will happen is if A is 0 and B is 1, right? Because not A will flip it, and B will be true. If A was 1, then not A would be 0, and then B would be true, but this ANDed thing would be not true. So that's kind of what you're doing, is if you want to check for A being 0, you can just use a not to say not A in parentheses and B. And so let's try to like walk through this example. So we have our XOR. Now let's go through our borrow. So our borrow, this is true, right? Not A and B. So this is true. So we have a 1. This is true as well. This is false. And this is false. And now remember, when we borrowed here, kind of like the same way as up here, when we borrowed here, we didn't really borrow 1, we borrowed a 10. So same thing here. You're borrowing, you're not borrowing from here, you're borrowing from the place above it. So if you add a 2 here, you're actually taking this 2 from here. So same thing, for the borrow, we need to shift it, because really we are borrowing from, you know, like this represents borrowing from here and so on. So whatever we get, we need to shift it. So we're going to get 0, 1, 1, 1, and we're going to get 0, 1, 1, 0. There we go. And now we do the same thing. So we XOR first to get the difference without the borrowing. So we get 1, 0, 1, 1. Now we do the borrow. So we get 0, 0. We borrow here, 1, 0. Then we shift this. And we get 1, 1, 0, 1. Hopefully I did this right. Okay. So, like I said, hopefully I did this right, but we'll see. So now we do the XOR again. So we get 1, 0, 1, 0. And for the borrow, now there is no more borrowing. There is no 0 and 1 combination, so this is all zeros. So what is this number equal to? Well, this is a 4 and this is a 1, so now we have 5. Right? And our original numbers were 12 and 7. So that is correct. So that's essentially what we do for the borrow is or I guess we already wrote it. So essentially you just get the difference, then you get the borrow, and then you shift the borrow left 1 to get the actual, like how much did you actually borrow, and you just keep doing this again until the borrow is 0 once again, kind of. So that's kind of like the subtraction addition you're doing. You're essentially saying I'm just going to do the addition without the carry, and then calculate the carry, and then add those together. Calculate all the carries combined, add those together, and same thing with the borrow. I'm going to do the difference, not including the borrow, and then I'm going to get the borrow and then subtract that. And that makes a lot of sense, right? Like it's totally fine to do it separately. And if you were to do decimal division, decimal subtraction, you could do it that way if you wanted to, right? You could just get like a total decimal subtraction and then the whole borrow bit, the whole borrow like number separately, and you could just keep subtracting the borrow until the borrow is 0. Like that would also work in decimal. Okay, so now we're going to code it up, and essentially what we are going to do is we're going to write 2 functions now, right? So this like sum and difference function, they're going to be very similar. And then, so we're going to write these 2 helper functions. We can actually write them even outside of this. So we can say sum was a function that takes a, which is a number, and b, which is a number, and it returns a number. And we can just say, like, while b is non-zero, we're just going to keep looping this thing. So we can do a destructure here. So we can just say, like, a, b. And so remember, for the sum, the a was a, x, or b. So the way to do XOR is this. And for the carry, it was a and b, right? Like, if you think about it, for a carry, it would have to be a 1 and a 1. So it's a and b. And b, and then it needs to be shifted left 1, right? Because it's not really carrying that bit, it's carrying the bit to the left. And then we can just return a here. Now we're going to do a difference. Pretty much copy paste with some small differences. So this is all the same. This is all the same, and this is the difference. Honestly, you could probably like write them in the same thing, but it's like 3 lines of code anyway. You could add another variable like sum or difference, but whatever. Okay, so remember this one is not a, and b has to be true. So there we go. Because right, in order for the borrow to be true, a has to be 0 and b has to be 1. So not a will be 1, and then if b is also 1, then that's correct. And we're shifting it again because once again we're not borrowing from the current bit, we're borrowing from the bit to the left. Okay, so now basically all we have to do is just write a bunch of if-else statements to get whatever the format of our numbers is to be, you know, positive plus positive, or positive minus positive, where a is bigger than b. So let's do that. So if a is less than 0, we can first check if they're both negative. So if b is less than 0, then essentially we're just saying, okay, let's just return the negative sum of negative a minus b, right? Or negative a, negative b. And that's pretty much just saying, like, if you had like -7 and -5, you're just saying, like, okay, let's make them positive, let's add them, and then let's just multiply the result by -1. And that would make perfect sense, right? You just get like 7 plus 5, 12, times -1, -12. And then you avoid all negatives. Because negatives are also language dependent, so like avoiding them makes things a lot easier. Because especially you're kind of limited here. Like if you have to do negatives, this is like super language dependent. I'm honestly not super familiar with how it works in TypeScript. But it's kind of annoying because, yeah, it's like it literally depends. You have to know like exact how negatives are handled in the language you're using it, and then it's kind of a super annoying problem. Okay, but positives are handled the same way in every language. So. Okay, so if b is negative, sure, we'll do this. Else if. So now we have to check if. So if a is negative and b is positive, is b the greater number? So if b is greater than -a, then essentially what we want to do is we want to do b minus a, but we want a to be positive, right? So we could just say like return difference. So if b is greater than -a, by the way, this example, this would be like if you're getting -5 and 7. So -5 and 7 would be the same as just 7 minus 5. So that's what we're going to do. So we're going to say return difference of b and then -a. So we are subtracting a from b, but we can flip them around, right? And in addition, you are allowed to swap numbers. So that's essentially what we're doing. And then also a number plus a negative number is the same as a number minus a number. So we're using both of those. Okay. Otherwise, a is greater than b. So if a is greater than b, then what do we have to do? So if a is greater than b, we need to make we need to like swap the bit, or not swap the bit, but we need to make a positive and b negative. Or I guess we need to make, we need to make a positive, and we don't need to make b negative. So this would be an example of like if you had -7 and 5. So if we did this with -7 and 5, the answer should be -2. And now we have 7 minus 5, right, which is 2, and then you just multiply by -1. So it's the same thing. So now that's everything for a, right? Like those are all the combinations you can have. You can have, you know, if they're both negative, if a is bigger or if a is smaller. Now we do the same thing for b, except we can skip a few. So very similar code here. You could probably make this like a little bit shorter, but it's fine. So if b is negative, we don't have to check for both of them being negative because they're handled here. But we have to check like if a is greater than -b, right? Then we can just we're trying to do a minus b thing here because a is bigger. So return difference of a and minus b. So this would be like if A was 7 and B was -5, you're essentially saying, okay, let's just do 7 minus negative, or yeah, it would actually be like, it wouldn't be 7 minus negative. Oh no, because we make it negative. We make it positive here. So if A was 7 and B was -5, we were saying basically let's just get like 7 minus 5, and that's the same thing. Okay. Else, so here basically B is bigger. So if B is bigger, then we want to do B minus A essentially, because we want B, because B is a bigger number. So we're gonna say let's just do this, and this would be the same as the 5 -7, right? 5 -7 is the same exact thing as 7 minus 5 times -1. So that's basically what we're doing here. Okay. And then finally, if none of them are negative, then we can just do the normal sum, right? If they're both positive, let's just do the normal sum. So sum A plus B. And there you go. So this is all the cases where now we either have a sum of two positive numbers or a difference of two positive numbers where A is bigger than B. If they are equal, also the order doesn't matter. Like 5 minus 5, it doesn't really matter in which order you have them because they're the same number, right? So that would just be 0 right away. And you wouldn't have a bar or anything because you're basically XORing. So XOR of two identical numbers is 0, and then the bar would be 0. Looks like we have a solution. And there we go. And you can see it's pretty efficient. So let's, like I said, this is one of those problems though that like if you haven't seen it before, good luck to you type of things. But once you have seen this kind of solution, that totally makes sense. Like we're just calculating the carry and the sum or difference separately, and we just add them together. Same thing with borrow, and have to figure out like what bit manipulation we can use to do that. So I think it's a very good bit manipulation practice. And if you haven't seen the solution, I would just bookmark it and try to do it in like a week and see if you can remember like what bit manipulations you need. Because when I first saw this, I couldn't do it, but then I bookmarked it and now I could like come up with it on my own. So here, yeah, so for the time, essentially we have to figure out like what's the time of our sum and difference. So I think it's like worst case scenario, it would basically be the number of bits of the number, essentially. Also not super easy to figure out, but yeah, basically the worst case scenario, it's the number of bits of the number. So this is technically like a 32-bit number, or it's technically, I mean, less than that. So you could argue it's like constant time because it's a 32-bit number, but I think the better scenario would be like saying it's a logarithmic function. So it's log of probably, I guess, like the bigger number, right? So max A and B, something like that, right? Log of the bigger function, and then space. It's of 1 because we're just using variables here. We're not using any arrays or anything. We're just using A and B in place, and yeah, just doing bit manipulation. So yeah, that's gonna be all for this one. Hopefully you liked it. Definitely one of the harder bit manipulation problems, but very good practice. And I think if you understand it, then you should know enough about bit manipulation for coding interviews because you're practicing like a bunch of different bit manipulations like XOR, NOT, and all the common stuff. I'd say the other stuff other than this, you're also practicing shifts. I think the only thing that's not covered in this problem is probably bit masks. So if you know this in bit masks, then you're probably like, that's all the bit manipulation you'll ever need. And yeah, so if you did like this video, then please like it, please subscribe to your channel, and I'll see you in the next one. Thanks for watching.